let's see how to train a simple neural network to classify digits from the MNIST dataset. I'll start by importing MNIST and Keras. Next, I'll load the MNIST dataset using its loadData function. And notice that it returns two tuples. The first one is for the train images and the train labels, and the second one is for the test images and the test labels. So of course, this is a classification problem. So for each of the images, we're also going to have its label. And the label is the correct class for each of the images. So let's explore a bit both the images and the labels. Let's start by looking at the shape of the images. And we can see that we have 60,000 train images, and each of these images is 28 pixels by 28. As for the test images, we have 10,000 of them, and each of these as well is an image of 28 pixels by 28. Let's use PyPlot to take a look at a few of these images. By the way, you can see that when we showed the shape of the train images, we didn't have a dimension for the channels, and that's because we only have one channel. Generally speaking, most images have three channels for R, G, and B, and that's because most images are color images, so they must have three channels for green, blue, and red. But when we are talking about the images in the MNIST dataset, these images are grayscale images, which means that they only have one channel. And that's why I'm going to show this image as a grayscale image. And here's the first image among the training images, and you can see that it's a not that great image of a 5. Let's take a look at the next image, and it should be a 0, I guess. And this is a 4, and so on. Now, if we take a look at the data of the image itself, we can see the values of the pixels themselves, and we can see that each of them is in the range of 0 to 255. Now, the test images are very similar to the training images, they are just different images. Now, generally speaking, in neural networks, it's better to represent the value of each pixel in an image as a value in the range of 0 to 1, rather than 0 to 255. So to make this conversion from the range of 255 to the range of 0 to 1, I'm simply going to divide each of the pixels by 255. And now we're going to have here and here the same images, but they will be represented as values in the range of 0 to 1. Let's now take a look at how our labels look like. And we can see that this is simply a vector of 60,000 values. This is to be expected, as we simply need to know for each of the digits which digit it is. So it can only be a value from 0 to 9. Let's take a look at a few of the images and their labels at the same time. So here we can see an image of a 5, and we can see that the label is 5. Let's see another image. And this is a really strange looking 5, and here is its label. Let's see another one. And this is a 3, and here is its label. Now, to work more conveniently with the labels, we're going to represent each of them as a vector of classes. What I mean by that instead of using only a single number, we're going to use a vector of 10 numbers. For the correct index in this vector, the one that the label actually represents, we're going to give the value 1. And for the rest of the indexes, we're going to give the value 0. A label with the value 7 will be represented as a vector of 10 values, where each of them are 0, except for the value at index 7, which will be 1. Luckily, we don't have to implement it ourselves, as Keras has a built-in function that will do it for us. This function is called toCategorical. So let's start by importing this function. And now we're going to use this function on our labels, and of course we have to provide the number of classes we have. In our case it's 10 because we can only have 10 different digits. Next, I want to flatten my images. So instead of having square images of 28 pixels by 28 pixels, I'm going to have my images as long vectors, where all of the pixels are represented in one long vector. So we're going to have the first row, and next to it we're going to have the second row of the image, and next to it we're going to have the third row of the image, and so on. To do that, I'll use the reshape function from NumPy. Let's start by getting the current shape of our images. And since we get a tuple, we can save each of these values in a different variable. And now I reshape the images. So we're going to have the same number of images, but each one of them is going to be represented as one long vector. Now that we have our inputs in the correct format, let's define the network itself. So as you can see, I want to have 3 layers in my network. The first layer is defined by this function, input. This is of course the input layer, and we have to specify the structure of this input. We do that by providing the shape parameter, and the structure of the input is of course a vector whose size is the number of pixels in each of the images. So the number of rows in an image times the number of columns in an image. Next, we're going to have an hidden layer. This is this layer. I chose to have 128 neurons in this layer, but of course this number is a bit arbitrary, and I could definitely go with 64 or 256 neurons instead. For the activation function, I chose ReLU, which is very popular and usually does a good job. The last layer is the output layer. It's going to have 10 neurons, of course, because we want to classify our images to 10 different classes. As for the activation function, I chose softmax. What this function does is represent the neurons in this layer as probabilities. So their sum is going to be 1, and each value says how probable the class represented by this neuron is. So for example, if a neuron in this layer ends up with a value 0.1, it means that the network thinks that there is a 10% probability that the class represented by this neuron is the correct class. And of course we have to import sequential from Keras. And we also need to import input and dense. Next, we need to compile our model, which will actually create the network and prepare it for training. We need to choose an optimizer, and I chose Adam, which is a very popular choice. As for the loss function, it represents how far the result of the network was from the required result. So as we said, the required result is always going to be in the form of 0, 0, 0, and then somewhere a 1, a single 1, and the rest of the values are 0 as well. So we want as results only vectors that are only zeros and a single 1. If the result of the network actually was such a vector, and the 1 was in the index of the correct digit, the loss would be 0. The chance for that is extremely low, of course, but we want to get as close as possible to it. The bigger the loss, the more drastic the changes to the network will be in the next epoch. Now that we have a compiled model, we can go ahead and train our network. So as you can see, we had to provide the training data and the training labels. I remind you that the training data is our flattened images, and that the labels are now represented as vectors of classes. We also had to define how many epochs we want, which is how many times the network will go over its entire training data. So in this case, we have 60,000 images that the network has to go over, and is going to go over it 8 times. The batch size determines how frequently the weights of the network will be updated. So the network is now trained, and it didn't take too long. Next, let's evaluate the quality of our network on the test data. So these are the 10,000 images that the network was not trained on. So I'll start by flattening the test images just like we did with the training images. And now I'll use the evaluate function to see how good the network does on the test data. And you can see that the loss that we get for the test data is about 0.08. This is much higher than what we got for the training data. Here we had about 0.02. This discrepancy might mean that we have a bit of overfitting for our training data. But as long as our loss is less than 0.1 for the MNIST dataset, our results should be reasonable. Finally, let's try to make a few predictions on the test data using our network. As an example, I'll choose the first 20 images from the test data. So here are the first 20 images, and we're going to use our network to predict the class for each of these images. Now, the predictions are represented as vectors of probabilities, but we don't really care about the entire vector. We only want the index in the vector whose probability is the highest. So to find this index, I'm going to use the argmax function. This function returns the index whose value is the biggest. And finally, let's also print the actual labels for these first 20 images, and this way it will be easy to compare the predictions of the network to the actual classes of these images that the network should have found. So here we can see the predictions of the network for these images, and here we can see the actual labels.